All right, so in this video, I'm going to go over the second problem on our fluids worksheet. And so if I pull it up here, it says we have a diver and he descends to a depth of 35 meters below the surface. It gives us the density of water as 1.025 kilograms per cubic meter. And the first two parts just want to know about the gauge pressure and then the absolute pressure. So the difference between gauge pressure and absolute pressure has to do with where you define your zero to be. So gauge pressure says that well, actually it's easier to start with atmosphere or with absolute pressure. Absolute pressure says that your zero is the vacuum. And so in order to figure out the absolute pressure, you add in all the other pressures. So for instance, if you're at the bottom of this ocean here, you would say, okay, well, there's the pressure due to the water above me, but then there's also the pressure due to the air above that, right? And so your absolute pressure, I'll just write it then. Your absolute pressure, P, is equal to the pressure above you, P naught, plus rho GH. Gauge pressure says instead of using my zero as the vacuum, I'm going to use my zero as the atmosphere. And so therefore the gauge pressure is what pressure do you feel minus the atmospheric pressure. Another way of putting that is just to say that the gauge pressure is just rho GH. And so what you could do then is just calculate the gauge pressure first. We have a density of 1.025 kilograms per cubic meter. We have a G value of 9.8, and we have our height of 35 meters. That's our gauge pressure. Plug all that in. Remember, your pressure is in units of pascals. And then in order to figure out the absolute pressure, you just add in the atmospheric pressure, which is about 101,000 kilopascals, or about 101 kilopascals, or about 101,000 pascals. All right, so the next part of the problem, well, let me bring it up here and I'll erase my board and then you can read, hopefully. Okay, so I'll let you read it here. But essentially what it says is that we have a rectangular aluminum plate with certain dimensions, and it's lowered into the water, and it wants to know the tension in the cable if it lifts the plate upwards at a slow constant velocity. Oh, he finds it. Okay, sorry, I had to read that again. He finds a plate at the bottom of the ocean, and then he wants to lift it upwards. And so I'm going to erase this here because this doesn't really help us with anything, does it? The important part about this, so let me erase my screen here now that you've read it. The important part about this is looking at the free body diagram and the forces. So assume that this is, a flat ocean floor. We have this rectangular plate right here. I'm not even going to look at the dimensions of it, but I know that I'm interested in the volume. I know that's the length times the width times the depth, and so I can figure that out. But either way, we have this plate down here at the bottom, and we hook something up to it. We pull it up like that, and so we want to know. What the tension. I believe that's what it asks for. We want to know what the tension in the cable is if you're pulling it up at a constant velocity. Remember, I hear the words constant velocity, and I hear that that means that there is no net force on it. And so therefore, I'm going to look at all my individual forces and then go from there. So let me draw in my free body diagram instead. So I have weight. I have weight that acts down. That's mass times gravity. Okay. I have the tension in the cable that points up, T. And then I also have one other force, which is the force that causes you to buy you. It causes you to go up in a water or in a fluid. We call it the buoyant force. And an important part about the buoyant force is that that force is always greater the greater your depth is. So in other words, if you have an object like this, you might say, okay, Pascal's principle says that there should be equal amounts of pressure on it. But really what's happening is that there's more pressure the lower you go, so therefore there's more pressure on the bottom of an object than on the top of an object. And so therefore, we have some buoyant force that also points up. So the buoyant force also points up. I'll put FB to represent that. And so I can say then that the tension plus the buoyant force minus mass times gravity is all equal to 0. I'm interested in solving for the tension. And so therefore I could say the tension is equal to mass times gravity minus the buoyant force. Okay, but of course they don't give us the mass of the object. We have to figure that out. What is the buoyant force? Well, let's see. Remember, we can say that the density is equal to the mass divided by the volume. And so therefore mass is equal to volume times density. And so this equation is equal to the density of the object times the volume of the object minus the density of the water times the volume of the displaced water. I'll put displaced water right there, times G as well. Now keep in mind that because this object is completely submerged, the volume of the displaced fluid is equal to the volume of the object. And so instead of writing V object and V displaced, I'm just going to write V object. And so this is equal to the density of the object times the volume times G minus the density of the water times the volume times G. I can pull out this volume times G, and so I can say that the volume of the object times the gravitational acceleration G times the difference of the density of the object minus the density of the water. Given all of those values, I can find the volume just by multiplying all the dimensions that they give us. G is 9.8, and then we're given what these two densities are, and so we can figure out what the tension is. And so the last part of the problem says, well, what happens now if you accelerate it upwards? And so let's see what happens then. So I'm going to erase this part right here. And so I'll go back to this point right here. And if we added an acceleration, we would say, okay, this is now equal to mass times acceleration, and therefore our tension is equal to mass times gravity plus mass times acceleration plus or minus the buoyant force right here. And so therefore, if we're going to accelerate it up, we're going to increase the value of tension. As long as your acceleration is positive, your tension will increase. And so the last part of the problem, the answer is just an increased tension with due to that acceleration. That makes sense. I mean, it doesn't matter if you're in a fluid or not, right? If you take an object and you yank it up really fast, the tension is going to be greater than if you did it very slowly and at a constant velocity. All right, so that's the answer to those.